All right. Good morning, everybody. I'm sorry about yesterday. Something had come up, and so I wasn't able to get that video up and loaded for you guys, and so I apologize for that. What I'm hoping to do today then is let's try to get through the introduction to pick up where we left off on Thursday of last week, where I was introducing to you what energy is and how we should approach the study of energy. What I'm going to do today then is we're going to finish talking about go ahead and put the timer here. I'm going to go ahead and finish up with this general discussion of what energy is, and then I want to get into the basic calculations, and hopefully, if we can get to the first part of Hess's law, and then what we'll do is we'll finish up with Hess's law tomorrow. Talk about the enthalpy, how we can use the changes in enthalpy and enthalpy of formation in order to get the same types of calculations done as well, and hopefully try to finish up with chapter 6 by tomorrow, and then start chapter 17 on Thursday and try to get that done. I am going to post a lesson this weekend just so just so we can get caught up and from yesterday and missing out on the lesson from yesterday. Okay. All right. So I didn't see any questions emailed to me today. So I haven't seen any questions emailed to me over the weekend. And so I'm hoping that the first lesson went okay for you guys with energy. I'm hoping then that you're able to be able to wrap up with understood what we did when we wrapped up chapter 12 as well. But please make sure then, if you have any questions, make sure you email me. Let me know if you need any questions answered. Email me and I will answer the questions on video. Okay. All right. So with that said, then we talked about energy and we discussed then the how the process of which energy flows. We left off then what we left off with then is we talked about how energy is the change in energy is a what we call a state function. And with the state functions, then what we are looking at then is that we are looking at then exclusively then the energy at the beginning and the energy at the end. And so we want to find then we're not too concerned with how we get from start to finish. We just want to know what the amount of energy we started out with and the amount of energy we end up with. And so we can calculate for the change in energy at that point. This is important because we really can't actually, when we talk about the changes in energy, we can measure that. Okay, so we can measure the change in energy that is absorbed by a system or given up by a system. So we can measure that. And so what we want to be able to do then is we want to focus in on that. Okay? And so that change in energy, and you're going to see then as we progress on today, and that change in energy is going to be basically comprised of work energy and heat energy, and we're going to see how those in turn are responsible then for the overall energy change of the system. From that, then we're going to talk about how the energy change of the universe, so that the system can change its energy. So make sure you understand then that when we talk about law of conservation of energy, we're discussing the overall energy change for the system and the surroundings as a whole, and that means in this the energy change of the universe. When we talk about that, energy change of the universe is constant. That means that there is no change in the overall energy of the universe. However, there can be an energy change in the system and in the surroundings. What we do know then is that the overall change in the system and the surroundings, whatever is absorbed or given off by the system or the surroundings, in the end they have to be they have to add up to be equal to one another. Okay? And so we left off then on Thursday with a basic definition of system and surrounding, and we need to be able to differentiate those two if we're going to talk about the energy flow. So essentially moving forward, what we will be doing then is we're going to talk about the nature of energy flow, how energy flows into a system, how energy flows out of a system, how energy flows into the surroundings, how energy flow out of the surroundings. So the system then, like we pointed out on Thursday, is that part of the universe. So if you can imagine the overall universe, the system is just that part of the universe where we're going to focus our attention, and we're going to look at that particular part of the universe, and we're going to examine the energy change in that particular portion of the universe. That portion of the universe could be an object, a person. It could be any type of process. It could be anything. It could be anything. And so what we're essentially doing is that we're going to zero in on that part of the universe, and we're going to take a look at how, as that particular object or that particular object of our focus, how that how its energy changes as it interacts with the surroundings. And so the surroundings then is everything else that is outside of that system. Okay, and so the system and the surroundings together is going to be is what comprises the universe. Okay, all right. So what we want to do then is when we talked about, obviously for our class, we want to discuss then chemical energy. Okay? And so what we want to do then is we want to talk about then the energy change that occurs during the course of a chemical process. Okay? And so that energy change, and what we're going to do then is as we study the energy change, we're going to focus in on the system. Okay? So we're going to focus in on the system right here. And with that said, that system then could be any type of chemical process. It could be a chemical reaction. It could be a physical process. But whatever it is, we're going to study then the changes in that chemical system. Okay? And so that chemical system then will involve bonds. It will involve phase changes, interactions between molecules. Okay? And so when we talk about that, then everything else, so that's what this system is going to be comprised of. System then is going to be whatever chemical process we were looking at. Okay. All right. So with that said, then let's take a look at what we have here. When we take a look at, when heat flows into the system, when we talk about heat flowing into the system, and for right now, let's hold off on the work part of this. We'll incorporate work into this in just a moment. Okay. But typically, when we talk about the energy change in a system, we're going to take a look at first and foremost the heat that flows into or out of the system. Okay, and so when we talk about a chemical system in which the requires heat, that means heat has to flow into the system. When we say that, in order for the chemical process to occur, what we're going to do then is we're going to say that that process is what we refer to as an endothermic process. That means heat is heat, thermic temperature basically goes up. Okay, so heat is going to be absorbed, temperature goes up. And so that means that heat's going to flow into the system in order to get the reaction or the chemical process to occur. The process then, what we're going to see then is that what we start out with is going to have less energy than what we end up with. The reason for that, and this is the reason why heat has to flow into the system in order to add more energy into the system, the chemical system, and raise the product up to a higher potential than the reactant. And so with endothermic processes, what we end up seeing then is that the products end up being at a higher energy. Okay? Now that can happen. Remember, we said that can happen. It will not happen spontaneously. This is not a spontaneously favorable process, and we're going to see that in chapter 17, but it can happen. It can happen because we're putting energy into the system. Where is this energy coming from? It's coming from the surroundings. Okay? So everything else around the system here. So here we're looking at the chemical reaction that forms nitrogen monoxide, NO, from nitrogen and oxygen. Okay? Energy has to be absorbed in order to form the compound here, the nitrogen monoxide, that is going to be at a higher energy state. Nitrogen monoxide then is going to be, it's going to have more energy than the reactants, nitrogen oxygen itself. So we can see then that nitrogen and oxygen are going to be more stable than nitrogen monoxide, NO, because it's at a lower energy potential. And so in order to get this reaction to occur, energy has to be absorbed into the system. We refer to that as an endothermic process. The opposite of an endothermic process then is a process in which then the reactants are going to be lower than the product. These reactions are what we refer to as exothermic reactions. That means temperature is going to drop, heat's going to flow out of the system. So that means then what we're going to see then is that heat is going to be pushed out of the system. Essentially what's happening here is the chemical system is generating heat, because what's happening here is that the reactants are at a higher potential than the products are. And so when the bonds break, bonds form, we're going to see that an overall release of energy in the form of heat. Okay? And so we refer to this process then as an exothermic process. Exothermic processes tend to be spontaneous. That means they will happen. Now remember, spontaneity means says nothing about how fast or how slow the process is going to take. It just tells us that if you let it alone, it's going to happen all by itself. Okay. All right. So with this said, with an exothermic process, then the products end up being more stable than the reactants because they are going to be at a lower potential. Okay. So energy then flows out of the system and into the surroundings. Okay. So that's how we define then exothermic and endothermic. Heat flowing in, heat flowing out. Okay. All right. So let's see if we can apply them and practice this a little bit. Let's go ahead then. Let's take a look at a process here. So, and let's use this to help us to also practice defining and identifying systems. So as we move forward, folks, you got to make sure then that you can define a system. That means you can identify what a system is, and then identify then whether heat is flowing into or out of the system. Okay, so let's go ahead and let's take a look at this problem. Okay, so I'm going to draw my box. Okay, so I'm going to go ahead and I'm going to draw my box, indicate then our system. Everything inside this box here is the system. Okay, and so what are we examining? And everything outside is the surrounding. So our system here is going to be inside the box. So I'm going to go ahead and write that in there. So this is, represents everything that's what we're going to examine, the process that we're going to examine. Everything outside is what we refer to as the surroundings. That is everything that is around the process. All right, so the process that we're examining here is the freezing of water. Okay, so let's go ahead and write out that process. Okay, so our reactant then is going to be water in the liquid state. Okay, so let's go ahead and make sure we understand that. And we're just going to write this in the form of a chemical reaction, but obviously this is a physical process. Okay? And that's going to be then water turned into ice, which is a solid state. Okay, all right. Now, with that said, let's imagine. So that's our system. Hopefully, you're able to identify this, because what we are examining here is the process of freezing of forming ice. Okay, so that is our system. That's what we are studying here. Okay, we're studying that. We're going to try to explain then whether this process involves the absorption of heat or the removal of heat. Okay, all right. So think about this. When you freeze water, do you have to remove heat? That means get heat out, or do you have to add heat in? Now, obviously, we all know this, and I'm going to draw this way. So heat has to be removed. That means heat has to flow out and away from our system. We got to remove heat. So this represents heat here. So that's heat energy right there. And heat is flowing out of the system. That means you have to cool it down. Okay, you have to cool it down. And so if you cool it down, at least you understand then that what we have at the beginning then, okay, is that the initial temperature of our system, and I'll just write it here, T initial, is going to be greater than T final. So the temperature is going to drop, okay, because heat's going to flow out. So in our system, then this is going to happen. So that means in our system, the initial temperature is going to be greater than the final temperature. The surroundings then, and let's now understand. Right now, I'm going to examine both. But moving forward, then when we talk about exothermic and endothermic, okay, we're going to focus on the system. But understand, we can apply the term exothermic and endothermic to both the system and the surroundings. And that's what I'm going to do here to get you to think about what these terms mean. Okay. All right. So heat's going to flow out of the system, which means then the surroundings. So this is in our system, okay, T final and T initial. In our surroundings, then T final is going to be greater than T initial, because the temperature is going to go up. Okay. So if heat is flowing from our system out to the surroundings, we expect then that the surroundings, the final temperature of the surroundings should be greater than the initial temperature of the surroundings. So we see that an opposite effect happening. Okay. All right. So that means then, to answer this question, is the freezing water, our system here, an endothermic or exothermic process? If it's losing heat, heat is flowing out of the system. This process then, the system then, is going to be an exothermic system. The process then is an exothermic process. So it is exothermic from the perspective of the system, but on the part of the surroundings, this is going to be then an endothermic process. So for the surroundings, the process then would be endothermic. Why? Because the surroundings is going to absorb heat. So the process, the freezing of water, is going to be exothermic for the system, and that's why that's what we have in the box here. But it's going to be endothermic for the surroundings. Okay, so whenever you have, if the system is gaining heat, that means the surroundings has to be losing heat. If the system is losing heat, the surroundings is going to be gaining heat. Again, like I said, then the overall, so the system can have a net change in energy, loss or gain. Same thing with the surroundings, net gain or loss in energy. However, the amount of energy lost and gained by either the system or the surroundings has to be, in the end, the same. That's in order to preserve then the law of conservation of energy. Okay. All right, very good. Let me go ahead and save this here. And so the process of freezing water, exothermic. It's going to be an exothermic process. Okay. All right. What I would like you to do then is on your paper, let's go ahead and let's take, I want you to try this here. I give you 5 different processes here, okay? And what I would like you to do then is take about 2 minutes, and think about with each process, is heat flowing into, first of all, identify the system, okay? And then go ahead then and tell me whether the system is exothermic or endothermic. You don't have to tell me what happens with the surroundings, but focus in on the system, okay? And tell me then, is the system undergoing a heat loss or heat gain? Is heat being lost or gained? And based on that, tell me then whether the system is undergoing an exothermic process or an endothermic process. Okay, so make sure you do that. So take about 2 minutes to try to get this done, and then I'll go over with you. Okay, so go ahead and take 2 minutes to identify work on this problem here. Okay. Okay. Hopefully you had a chance to get this done. I'm going to go ahead and I'm only going to work out a couple of these for you. Let me go ahead and I'm going to open up a whiteboard here really quickly. And again, I'm going to draw the box here. So let's go ahead then and open up my whiteboard here, and let's examine each one of these systems together. Okay. All right. Let me go ahead and move this over. Okay, let's take a look at the first one, you guys. All right, so the very first one we were given then is we were told then that your hand is, it gets cold when you touch the ice. Now here, I do make it a little bit easier for you. I tell you what the system is. So let me go ahead and draw my box. Okay, so there's the box. I'm sorry, box. Again, you don't have to do this. I do this just, this is how I helped me to learn this. So, to really make sure I can focus in on the system and the surroundings, because later on, you're not going to be told what the system is. You'll have to be able to identify it. And on the AP exam, they especially do not tell you this. Okay, so it helps you to do this here. Okay? And so I'm going to go ahead and draw my box, okay, identify the system. Okay, inside the box, surroundings, outside the box. Okay, so there it is. We have the system and the surroundings. Okay, so we said then the underlying process. So the hand. Okay, so we're looking at the energy flow for the hand. Okay, so the hand here. Okay, so let's go ahead and talk about that. This time, the hand is holding on to a piece of ice. So when you hold the piece of ice, think about this. Does the ice feel hot or does it feel cold? And I don't mean to ask such a basic question, but you have to understand this. Okay? It feels cold. It feels cold for one very simple reason. That's because it's absorbing the heat from your hand. Okay? So that means then the ice is part of the surroundings here. Okay, so if you're holding the piece of ice and you feel cold, that's because heat is flowing from your hand, from the system, out to the ice, which is the surroundings. Okay, so let's consider that. So heat then is going to flow out of the system. Okay? If heat flows out of the system in the surroundings, then we know that the process then has to be, and we talked about this, an exothermic. This is an exothermic process. Okay, so hopefully you're able to identify that. Okay, so heat flows out of your hand. Now the reverse then is if you touch something hot, the object that is hot is transferring heat into your hand. That's why it feels hot. That would be then an endothermic process. But the piece of ice then feels cold, not because ice is cold. It's at a lower temperature than your hand. And because it's at a lower temperature than your hand, the heat from your hand is flowing into the ice, and that provides sensation of cold because you're losing heat from your hand. Okay. All right. So hand fetching ice, that is an exothermic process. Okay, let me go ahead and say that. And let me go ahead and let's take a look at the next one. So I'm going to go ahead and I'm save this here. I'm going to erase the hand, erase the exothermic, erase then the heat flow, erase the heat. Let's take a look at the next process. Okay. All right. So the next process we were told then is the ice gets warmer as you touch it. So we're going to change the direction of observation. Now this time then we're looking at the ice. Okay. So if ice is pulling heat from your hand, if ice is pulling heat from your hand, can you imagine then what's happening is that heat's going to be flowing into the ice. So you can imagine then holding the piece of ice, the heat from your hand is going to flow into the ice itself. Okay, so the heat from your hand is flowing into the ice, And if heat flows into a system, okay, that means then that system then is undergoing an endothermic process. Okay, so this is an endothermic process as we take a look at this. Okay? So hopefully you are able to get that. Okay, let me go ahead and save this and share it with you as well. Hopefully you're able to do that. And what I'm going to do then is I'm just going to go ahead and provide you. I'm going to go ahead and open up, and I'm just going to go ahead and give you the answers for the remaining three. And if you have any questions about it, please, like I said, email me so that way then I can go over it. Okay, so hand touching ice. That's going to be then. Whoops, sorry, this. That. Okay, that's going to be an exothermic process. Ice getting warm, we said that's going to be endothermic process. Water boiling in a kettle. Now, just think about this. In order to get water to boil, what do you have to do? You have to add heat into it. You have to add heat into the liquid water. And so if you're adding heat into it, it has to be an endothermic process as well. Water vapor is condensing. I'd be interested to find out how many of you were able to get this. But in order to get water vapors to condense, and make sure you understand this, you have to drop the temperature. You have to drop the temperature. And that means then the water vapor is going to be losing heat in order to get that. So that's going to be an exothermic process as well. So the water vapor itself condensing, water has to give up its heat in order to condense. And again, I'm curious about this because we know then that when we talk about condensation, a lot of folks think about you got to drop the temperature in order to get that done. You have to drop the temperature because water has to give up its energy in order to condense on the cold pipe. Okay. Okay. So with that said, then let's go ahead and ice cream melting. Ice cream, in order ice cream to melt, has to absorb heat, so therefore it is also going to be an endothermic process. All right. So just, real quick, going back, water evaporating, on the other hand, is going to be an endothermic process. If condensation is an exothermic process, evaporation is going to be an endothermic process. And so that means then if it's an endothermic process, it means it's absorbing heat. So therefore, if you have water, for example, when you sweat, and I've talked about this before, if you've had me, when you sweat, the sweat on your head or on your forehead, that actually serves to cool you down because it's absorbing heat from you in order to evaporate. Okay? But with that said, then please email me if you're interested in that. All right. So with that said, let's go ahead. Let's continue on. Let me ask you to take a look at this particular problem here, and what I'd like to do then is for these two here, I want you this time to define the system and the surroundings, and then describe them whether it's exothermic or endothermic. Okay. So take about 2 minutes. This time you have to identify the system as well as identifying whether that system in this particular process that they're describing here, is it the exothermic or endothermic? Take about 2 minutes to answer your question on your paper, and then please make sure you submit it before the due date, and then we'll talk about it in about 2 minutes. Okay, so go ahead, take 2 minutes to answer this question. Okay, let's take a look at this, folks. I'm going to pull up my whiteboard again in order to get this done because I want to draw my box and I want to make sure that I identify what's in the box and what's outside of the box. All right, so let's go ahead then and let me erase this really quickly. So we have our system, we have our sides. Let's take a look at the very first process. Okay, so this here. Okay, all right. So we have methane burning, the very first methane burning in a Bunsen burner in a laboratory. Don't let all the words get in your way. Okay, the process, the system here, the chemical process that we are looking at, or we are studying, is the burning of methane. Okay, so the burning of methane is going to be this reaction. It's going to be CH4 plus O2 forming CO2 plus H2O. That is our system. Okay? So what we're doing then is we're looking at this process here of burning methane. Now, so that's our system. The surroundings then is everything else around it. Okay, everything else around it. When you burn anything, okay. Now a lot of people get confused by this because they think, well, wait a second. When you burn something, the first thing you have to do is that you have to light it up. You have to ignite it in order to get it to start burning. Paper, for example, wood, methane. But understand this. Yes, you are right. You got to input that energy. Remember, we were talking about activation energy. So what you have to do is that spark or that amount of heat initially allows the process to overcome its activation energy. And then from there, it produces, because this is going to be a process in which the products, and we saw this not too long ago in a few slides back, the products here are lower in energy than the reactants, making this then an exothermic process. And the reason why it can continue to burn, and so the answer then is going to be exothermic. There is our process. This process then is an exothermic process. But the reason why it continues to burn is because it generates heat. Now, just think about it. When you're sitting next to a Bunsen burner, or when you're sitting next to a fire, yes, you get it going, but afterwards it continues to produce heat, light energy by itself. Okay, the energy, the chemical reaction itself produces that energy. So therefore, this process, even though it starts out and it needs to a little bit of energy, it starts out then as afterwards it is an exothermic process because it generates heat, and the heat flow out to the surroundings. So if you're sitting out here, or if you're right next to the Bunsen burner, you can feel that heat being generated. Okay, all right. So that then, let me go ahead and save that. That is going to be the burning of methane. Okay, let's go ahead then and let's take a look at the next one. I'm going to go ahead and erase this really quickly, and then let's use this box again to help us here. And so practice this, folks. I'm going to assign the homework for tonight, and please make sure you get that done in order to help you to practice this. Okay, so homework from chapter 6. But practice this, and then, like I said, make sure you email me your questions. Jim. All right, let's take a look at the next one. We have then water drops sitting on our skin after swimming evaporates. Okay. All right, so I just had talked about that. So the process of evaporation then is water, okay, going from the liquid state to water in the gaseous state. Okay, so that's the process of evaporation. Okay, so in order to have water evaporate, okay, and make sure you keep this in mind, you have to add heat. Just think of boiling. Okay, so you're going to add heat to this process here. So you're going to add heat to this process in order to get water to turn from the liquid to the gas state. So if you're going to add heat to your system, okay, that makes then the system then is going to undergo an endothermic. Oops, sorry, endothermic process. Okay. All right. So please practice then, and so that's the whole idea behind how sweating is is a cooling process, even though the process by which that occurs is an endothermic process. You absorb heat, but again, understand this: the water droplets, you can imagine it's the sweat droplets on your forehead. Okay, it is going to be absorbing heat from your body here, which represents the surroundings. And as it absorbs the heat from your body, that's what allows your body to cool down. So sweating, this process of evaporation, actually is a cooling process. Okay. All right, very good. So let me go ahead then and let me save that as well. Okay. All right. Let's go ahead then and let's continue on. Let me go ahead and try to finish up with this section here. So. Okay. All right. So with that said, let's go. Let me go ahead and give you the answers to that. Hopefully you got that as well. Whoops. Okay. All right. Let's go ahead then and let me ask you to do one more problem here. Okay. Hydrogen gas and oxygen gas, you are told here, reacts violently to form water. So the reaction is going to form water. The question then is, which is going to be lower in energy? Okay, the hydrogen in the gas or the water itself? Okay, so reacts violently. Use those to help you. What I would suggest you do then is to draw the box. I would suggest you identify the system, okay, and identify whether the system is undergoing an exothermic or endothermic process. And based on that, and based on what we talked about earlier, okay, with the exothermic and endothermic processes, what does that say then about the reactants, the energy of the reactants versus the energy of the product? Okay, so take about 2 minutes, you guys, and answer this question, and then unpause the video, and then let's compare answers. Okay, so take about, I don't think it'll take you 2 minutes. It'll take about 2 minutes. If you need to rewind the video to find the answer, please go ahead and do so, and then we'll talk about it. Okay, so 2 minutes. Okay, Let's go ahead and let's take a look. I'm not going to switch on the switch over my board. I have enough room here, so I'm going to draw my box right here. Okay, so I'm going to draw my box to represent my system and my surroundings. Okay, so let's go ahead and let's do that. Okay. All right, so we have then, let's go ahead and write this in here, the system. Okay, and our surroundings out here. All right. The process then is the chemical reaction. It's the reaction between hydrogen and oxygen to form water. Okay, so it's going to be then hydrogen plus oxygen to form water. Okay, it's going to be 2, 1, 2. Okay, all right. So with that said, and we talked about this before. I think you've had it before. We talked about this. This is a very violent reaction. Violent, then it produces a lot of energy. And I know that if last year we didn't get a chance to run this reaction, but if you were to run this reaction, and we do run this reaction in lab, you see then that you have this you have this popping sound, this miniature explosion where you form a little bit of light, okay, and you form the sound energy, the popping, okay. And if you had a chance to if it was big enough, you would feel the heat as well. Okay? So in this particular process, then, a lot of energy is being produced. That means then energy, not only in terms of heat, but we're only going to represent it as heat here, is going to be moving out of the system. Okay? And so therefore, this process is an exothermic process. Okay? So it's an exothermic process. And remember, we said then that if we take a look at then for all exothermic processes, the product will be lower in energy than the reactant. Okay? And so we draw the energy diagram here. If we draw the energy diagram here, what we're going to notice then is change this here real quickly. Okay? If we draw the energy diagram here, and energy is increasing as we go up. Okay, energy increases as we go up. What we're going to notice here then is if we draw the energy levels here, okay, the reactants then will be higher in energy than the product. So therefore, hydrogen and oxygen actually occupy a higher energy position. They have a higher energy potential than the water that is produced. That's why this process then releases a lot of energy. So therefore, the change in energy, the potential, we have a drop in potential energy here. Okay, let's go ahead. Yeah. So that then the change in energy is going to be then a negative one. Okay, so that's what we're going to see then. The delta H here, I'm sorry, delta E. It's going to show then that it's going to be a lower, you have a lower energy state for the product, for the water here than the reactants. Okay. All right. Let's save that really quickly. Throw that out. All right, so water then ends up being the more stable, lower in energy than the reactants itself. Yep. All right, so hopefully, again, the idea then is to be of this exercise is to identify a system, identify whether that system, and again, we're focusing only on the system from here on out, identifying whether that system is going to be absorbing heat energy. In that case, then it is undergoing an endothermic process, or the system is undergoing is giving off energy. In that case, then you have then an exothermic process. So to summarize here, this is what you should be able to do. Okay, the energy gain. So with that said, then we need to make sure we understand once you have identified this, the amount of energy that is the energy change itself. Okay, the amount of energy change that the system undergoes has to be exactly the same amount of energy that the surroundings will absorb. Okay, so the system will undergo a chemical energy change, and then the surroundings will also undergo an energy change as well. It has to go somewhere. That energy has to go somewhere. You can't just make it disappear and go away. Okay. All right. So with that said, then if you take a look at this for an exothermic process, the energy change is going to be negative, which means that it's going to be losing energy. So make sure you keep that in mind. That whenever you have an exothermic process, okay, for an exothermic process, let me go and write this here. Okay, so for an exothermic process, the energy change in delta E will be negative, and that's what this symbol means right here. That means then the way you want to think about this is that it is, if it's negative, it's losing energy to the surroundings. Okay? So the system then, if the system then is an endothermic process, the change in energy will be positive, which means then if you can imagine that we are adding, and this is a very good way to think about this, we're adding energy to the system. So if we're adding energy to the system, so that if delta E of the surroundings of the system is negative here, you can imagine the delta E of the energy change for the surroundings, and we'll write that as, it's going to be then positive in the first case for an exothermic process, delta E for the surroundings then, if for an endothermic process, it's going to be negative. So the two signs will always be opposite, and we're going to learn about this a little bit more, and I'm running low on time here. We'll learn about this a little bit more tomorrow, that when we talk about energy and energy changes, we're going to have not only the amount of energy, that is the magnitude of energy change and energy loss, but also there will be a direction to it as well. So that means that energy is not a vector quantity. Energy is actually a scalar quantity, okay? But energy is not a vector quantity, but we do assign a direction to it as well, either into or out of the system. And it'll always be from the direction of the system. Okay, so with that said, then energy gain, energy lost by the system has to be exactly equal to energy gain, energy loss of the surrounding. This is what this is. Let me go ahead. And this is a basic statement of the first law of thermodynamics, which basically tells us again that the overall amount of energy, it has to be constant in the universe, but in application to what in applying it to what we have been talking about, the energy change in a system, the energy change in the surroundings has to be exactly the same. That is the first law of thermodynamics. Okay? And so if you do it that way, okay, the overall energy of the universe stays constant. Okay. Now, with that said, thermodynamics. Then, when we're going to focus on heat and energy, heat and work energy here, and tomorrow, then we'll talk about that in a little more detail, right? But this can be applied then to any type of energy conversions that we can talk about: sound energy, heat energy, mechanical energy, and so forth. Okay. All right. So with that said, then what we'll do tomorrow in the lesson for tomorrow, I will continue on with the discussion. I will start the discussion of what's called internal energy and how we can calculate for the energy change using heat and work. Good. All right. And then I'm sorry, a preview also pressure volume, and we'll also talk about pressure volume as well. Okay. All right. Very good, folks. Have a good rest of your day. And again, I apologize for yesterday. I'll make it up for you by posting a video over the weekend for you as well. Okay. All right. So I'll see you folks tomorrow. And please remember, make sure then that if you have any questions, you email me your questions. Okay. All right. Have a good rest of your day, folks. Bye.